Okay, the activity series. We're all pretty aware that some elements, compounds, we could summarize them all as calling them species, are more reactive than others. We've seen elements so reactive, like lithium, like sodium, that you can put them in water and they will burst into flames and spark. And then there are other things that will hardly react at all, like graphite, like platinum, like gold. So we know that some elements are more reactive than others. We're in the topic of redox, and so we can split reactivity into sort of two major categories. We can look at species that act as oxidizing agents. Remember that those are species that cause other reactants to lose electrons. So they are species that steal electrons from others and then themselves get reduced. We can also look at things that are called reducing agents, species that cause other reactants to gain electrons. And so those are species that give electrons to others and get oxidized. If we want to think about in terms of like elements, which types of elements fall into these categories, well, nonmetals tend to be pretty good oxidizing agents, especially the halogens. Halogens are group 17. They're the ones right before the noble gases. They have especially high electronegativities and electron affinity values, and so they have a very strong attraction for electrons. If you have a strong attraction for electrons, then you're going to be good at stealing electrons from others. So what we would say is that the strongest oxidizing agent possible is fluorine, F2. It's that we all know that fluorine is a super reactive element. It's got the highest electronegativity, the strongest attraction for electrons. So the vocab we would use is we would call it the strongest or the most powerful oxidizing agent. It is the best at stealing electrons from things. On the other side, reducing agents, the type of elements we would predict to be reducing agents are those that give away their electrons easily. So those are the metals. Metals, and especially the alkali metals, group 1, the things like sodium, lithium, potassium that I just mentioned. Metals are good at giving away electrons. They have those delocalized electrons. And so the more readily they give away electrons, the more reactive they are. They're good at losing electrons, essentially. And so the strongest reducing agents are things like lithium, sodium, potassium. Okay? Now there's lots of polyatomic ions and things that will also fall into these categories. Things like that we've seen a lot of in our reactions, like manganate and dichromate. Things like that are powerful oxidizing agents. They have lots of oxygen in them, and so they end up being good at giving away oxygen and at losing electrons to other things. But for now, we're going to focus on the elements. Nonmetals are good at stealing electrons, and metals are good at giving away electrons. The ranking of elements and ions for their ability to act as reducing agents is known as the activity series, with the strongest reducing agents listed at the top and with strength decreasing down the list. This is in your data booklet, table 25. It is the activity series. So based on this list, it's quite a long list, what it means is that lithium is the strongest reducing agent out there. Okay? Cesium slightly less so, then rubidium, potassium, and so on. And we go down and down and down. And at the bottom, we get the very unreactive, very stable metals. At the top, we get the strongest reducing agents. These things are extremely reactive metals, the ones that will react with water. And then in between, we've got a whole range. And so as you go up, things are getting more and more and more reactive. And the things at the bottom are very stable. That's why the things at the bottom are what you end up seeing in jewelry: gold, platinum, palladium, silver, even copper, because they are very unreactive. They stay shiny longer. So there's really two ways that you'll be using the activity series or doing questions with activity series. The first is using a given series, like if you were asked to use table 25 of the data booklet. You can use the activity series to make predictions about whether or not certain combinations of reactions or of species will react spontaneously, whether or not they will react. We're going to go over how you can do that, but essentially you can use it to predict whether or not a mix of things is going to react with each other. The second thing that you'll get asked to do is you'll get asked to make your own activity series. If you test different combinations of reactants and you see whether or not they react together, you can use that data to rank how reactive the elements are. We're going to start with this number 2, making our own activity series. So the question would be, do copper and silver ions react spontaneously? Or will silver react spontaneously with copper ions? So if you think about it, if we're putting copper into a solution that contains Ag plus ions, right? A very common solution of silver ions is called silver nitrate. So what I'm showing you here is the net ionic equation. I've removed the nitrate. So it turns out if you put a piece of copper into silver nitrate solution, if you give it enough time, it will end up looking like this. The solution will turn blue, which indicates the presence of copper ions, copper 2 plus ions, and the copper will get covered in all of this shiny whitish stuff, which is silver. So do copper and silver ions react spontaneously? Yes, they do react spontaneously, and the products are pretty clear when you do the reaction that silver metal is made and copper 2 plus ions are made. In order for this reaction to technically be balanced, based on redox and exchanging electrons, I need 2 of those silvers. So do they react spontaneously? Yes. Now, if you actually look at what's happening in terms of the half equations and the oxidation states, you can see that copper starts off as a 0 and it ends up as a 2 plus, which means that the copper lost electrons. So copper, as it goes here, it lost electrons. It's hard to write with this thing. Okay. Now, if it lost electrons, that means it got oxidized. And if it got oxidized, it means it's acting as the reducing agent. So copper, summarize, it lost electrons equals got oxidized. That equals it's the reducing agent in this reaction. Okay. So another way to put it is copper is able to reduce silver ions. Okay, that's what we've learned from this. If you look at what happened to silver, silver starts at plus, it ends at 0, which implies it gained electrons. So then the next question, if we're comparing how reactive these elements are, is to ask about the reverse. Will silver metal react with copper ions? Well, the answer to that is no. There would be no reaction if you do this. You could put silver metal into copper ions and there's no reaction. So what does that tell us? Silver do not reduce copper ions. Okay? There's no spontaneous reaction here. Just nothing happens. The silver metal just sits in the copper solution. So if we pull these two pieces of information together, one, copper is able to reduce silver ions. If you put them together, the copper will lose electrons to the silver ions. If you put the opposite combination together, the silver cannot reduce the copper ions. So out of those two metals, which is the stronger reducing agent? From the information, I would say copper is a stronger reducing agent. It was able to give electrons to silver ions, and the reverse didn't happen. Silver cannot reduce copper ions. So in our series, we would rank copper above silver. So in this last step, the mini activity series from our observations is that we would say copper ranks higher than silver. And we'd have a little arrow that shows increasing activity or increasing reactivity, and it goes like that. Now, one thing that we didn't mention before is you could also look at the same reactions in terms of oxidizing agents. So if the copper here is the reducing agent, that means that the Ag plus is the oxidizing agent, which makes sense because it got reduced. So usually we're going to look at reactions and the activity series ranks reducing agents, but sometimes the questions will ask you about the oxidizing agents. So Ag plus is acting as the oxidizing agent, and Ag plus can oxidize copper. So that's what we learned from the first one. The first reaction tells us both that copper is able to reduce silver ions and that silver ions, Ag+, are able to oxidize copper. So if we look down here, we learn two things. We learn that silver cannot reduce copper ions, and we learn that copper ions cannot oxidize silver. Okay. So whenever you do a reaction, you learn two things at once. If they do react, you learn, okay, copper is a stronger reducing agent, and Ag+ is a stronger oxidizing agent. If they don't react, we learn that they're weaker agents. So from this one reaction, I learned that copper is a stronger reducing agent than silver. And in both of these cases, I'm referring to the metal, the pure element. But I also learned that out of the two ions, that silver ions are stronger oxidizing agents than copper ions. It's just based on which reactions are happening and which ones aren't. The silver ion seems to be able to pull electrons off of copper, and the copper ions can't do that to silver because there's no reaction. So I get this little series. It would be written like this, and even though it's not written in, I could know that on the flip side, going down, if I ranked their ions, I would get, if I compare copper 2 and Ag+, the increasing activity actually decreases, or is increasing as we go down. So when you look at an activity series and it tells you that you have increasing activity going up, increasing activity up is the reducing strength for the metals. So copper is a stronger reducing agent than silver. But at the same time, you can use that to know a little bit about the nonmetals. That over here, going down, you have increasing activity or increasing oxidizing strength for the metal ions. Okay, so continuing on, if we did another reaction, silver and gold, so we could do it both ways. And I gotta edit that, there we go. So I can put silver into gold ions, and I can put gold into silver ions, and we want to see, well, which one will take place. So it turns out that if you put silver into gold solution, you would end up making gold metal, and you would get out silver ions. So this reaction is a yes. This reaction does happen spontaneously. And that means this reaction is a no. If one of these reactions happens, the other one shouldn't happen. Okay, so what can we take away from this? Same things we took away from the last one. Ag can reduce gold ions, and gold ions can oxidize Ag. From this, we learn that gold cannot reduce silver ions, and silver ions cannot oxidize gold. Okay, so we're learning these bits of information at the same time. So now we could actually add to that series. How can we use this info to add to our activity series and make other predictions? So what we did before was we already knew. Let me get out of here. So we already knew that in terms of reactivity, we would rank copper above silver. Based on this new information, that Ag can reduce gold, and gold cannot reduce silver, based on how we did it before, we should rank gold beneath silver. So copper can reduce the silver ions, and the silver can reduce the gold ions. So now we have a bigger series based on two sets of reactions, showing increasing activity this way. If you notice, it's also going to work going down for their ions. So over here, we've got the copper ions, then we've got the silver ions, and the strongest oxidizing agent would be the gold ions. So our series, if you got asked to make an activity series, would be the thing on the left, copper at the top, the strongest reducing agent, followed by silver, followed by gold. Over here, it's not shown in the regular series, but it's what you need to be able to figure out, which is that going down, we have the stronger and stronger oxidizing agents. So the strongest agents written here are copper. Out of all these things, copper is the strongest reducing agent, and gold ions are the strongest oxidizing agent. What's also really cool is that even though I didn't carry out the reaction between copper and gold, I can now predict that if I put copper with Au+, or if I put Au+ with copper ions, I can predict which one is going to happen and which one is not going to happen. Right? So it's one of those sort of transitive properties that you can carry it over. We know that when we put them together, we put copper and we put copper and silver together on the first page, and that reacted. And then we put silver with gold, and that reacted. So if copper can give electrons to silver ions, and silver can give electrons to gold ions, then what we can predict from that is that if I put copper with gold ions, that should also happen. Copper seems to be the best at giving away electrons, even better than silver. So copper should definitely be able to give electrons to gold. So in my reactions down here, I would predict that this happens. So we would predict yes, spontaneous. And for this one, we would predict a no, not spontaneous. It won't happen at room temperature under normal conditions. And we can look at that the other way. We knew that already that silver, I'll do these in red, we knew already that some of these reactions wouldn't happen. We knew that silver and copper plus is a big no-no. That reaction doesn't happen. And we knew that gold and silver ions is a no-no. That doesn't happen. So if those combinations don't work, when I put gold with the copper ions, it's definitely not going to work. So the series ends up being this nice tool for predicting which reactions can happen and which reactions can't happen. It's based on how reactive they are. Putting more reactive reducers with more reactive oxidizers will take place. Putting less reactive reducers and less reactive oxidizers together won't react. And so from here, this is the activity series. The elements on the left are the strongest reducing agents. So lithium can give electrons to any of these elements' ions that would be beneath it. So if you created the alternative series here, cesium and rubidium and potassium and barium, going all the way down the list, but I'm going to just stop there to make it reasonable. Lithium, because it's the best at giving away electrons, lithium can give electrons to cesium. I know that it can give electrons to rubidium. I know that it can give electrons to potassium. I know that it can give electrons to barium. So all of these reactions would take place, and I would predict that yes, they happen spontaneously. At the same time, I would know that any of these metals down here is not able to give electrons to the lithium plus ions. Lithium plus ions will not get reduced. I meant to make all that red. So none of these reactions are going to happen up the hill. So cesium can't do that. Rubidium will not give electrons there. Potassium will not give up. So those are big no-nos. Okay. So electrons always go down the series. So we can predict spontaneous reactions as electrons are given down the series from stronger reducing agents to weaker reducing agents ions. Okay, and those are the types of things that you'll be asked to do. You'll be given data about reactions taking place, such as this and this, and you'll be asked to put it together into a series and know that copper is more reactive than silver. It's a stronger reducing agent, and that silver plus is a stronger oxidizing agent than copper 2 plus. You also can be given the series and be asked to predict which reactions will take place spontaneously. Like lithium will react spontaneously with these barium 2 plus ions, but barium will not react spontaneously with the lithium plus ions. So after we do a couple of these problems, you start to see how they piece together. They're fairly straightforward. But that's your introduction to the activity series, which will have further applications down the road.